Hello. In this video, we'll cover various ways to create efficient dynamic blueprints with collision setups, as well as how to use these blueprints to populate a level. When creating a dynamic collision blueprint, it's essential to consider its intended context. Two primary factors should be taken into account. One, is the object a significant part of the simulation, or just a background object? Two, will the prop interact in detail with other objects, or does it simply need to create an immersive effect? To demonstrate this, we will go over three examples in increasing complexity. Example 1. Creating a cylinder. Let's start by looking at a simple cylinder object. Suppose we have a basic object that could be represented as a cylinder. In the content browser, we already have two blueprints with a cylinder mesh. The first uses a convex hull to approximate the cylinder, which captures its shape well. The second blueprint uses an implicit shape, defined by a mathematical equation, which takes more time to align but provides better contact precision in simulations. In our test level, we'll place both cylinders side by side on a ramp. The implicit cylinder rolls down the ramp without resistance, while the convex hull cylinder experiences some friction. The difference in behavior is illustrated in the following diagram. Implicit shape, left, contact points are always perpendicular to the cylinder surface and ramp, passing through the cylinder's center of mass. As a result, the cylinder rolls without friction. Convex hull, right's contact points are normal to the ramp but not always to the cylinder, generating a friction-like force that opposes the motion. Both methods are valid. It just depends on how you intend to use the blueprints. Example 2. Creating a specialized shape for a tire. For vehicle simulations requiring realistic behavior, a standard cylinder may be less accurate than a specialized wheel shape. Here, we demonstrate the difference by comparing a simple cylinder with a specialized wheel shape on a ramp. The specialized wheel maintains a straight path, while the cylinder veers slightly. The behavior is explained by the forces acting on each shape. For a cylinder, two reaction forces create unequal friction forces due to the plane's tilt, causing a net turning torque. For a chamfered cylinder, a single normal force passes through the wheel's center, eliminating this torque. Specialized shapes can also improve accuracy, especially for analytical tire models like the Pasejka or brush models, which assume an elliptical contact patch. These parameters, often provided by tire manufacturers or custom-made in simulations, are harder to model with a simple cylinder. Example 3. Making an optimized compound shape. When working with complex shapes, using a single collision primitive or convex hull may not yield the desired behavior. In these cases, we can either use automatic convex hull approximation or manually combine multiple collision primitives for better accuracy. For example, let's model a lamp prop. The automatic convex hull approximation results in 13 convex hulls, which accurately represent the lamp's shape, but may overcomplicate the simulation. Additionally, small parts like the lamp stem can cause collision issues. A simpler alternative might involve using an implicit capsule for the stem and two variable radius cylinders for the shades. Testing these props in the level will highlight how multiple solutions can work for the same object. Once we complete our prop library, we can start populating the final level. Here, we'll use an architectural level, providing a complex environment to test our prop behaviors. Placing props in a level is an interactive process. We place one of more blueprint, and we run the level, and we repeat the process until we get the desired results. In the next video, we'll explore the rigid body, the second fundamental component of a rigid body library. The behavior of a rigid body can vary significantly based on its parameters, often resulting in unexpected effects. A basic understanding of rigid body dynamics can be extremely helpful for fine-tuning these behaviors. Thanks for watching.